Hello fellow students, in this video I will discuss the section 2.2 of Peskin and Schroeder's Introduction to Quantum Field Theory, in particular the subsection about Lagrangian field theory. If you are like me, you might be familiar with the Lagrangian mechanics of the classical physics, but you may never have thought of the fields in the lens of Lagrangian formulation. If so, it might be a bit jarring to be suddenly exposed to the Lagrangian of a field, and everything seemed foreign to you. So, right now, before diving right into the Lagrangian field theory, I would like to review Lagrangian mechanics in preparation to move on to fields. The goal of this video is to look back how might we, quote, invent Lagrangian mechanics or the Euler-Lagrange equation ourselves. This will ready ourselves to tackle the Lagrangian field theory in the next video. So, back to Lagrangian mechanics. Alright, let's say we have an object at initial time t sub I, position x sub I, and velocity v sub I. Then, say we know after some time, at final time t sub f, its position is at x sub f and velocity v sub f. The main question is then, how did the particle evolve from the initial state at time t sub I to the final state at time t sub f? Which path did it take? Now, from what I've heard, the Joseph Louis Lagrange, it was inspired by the Fermat's principle. That is the principle that light takes the path of least time. It minimizes time. So perhaps this is the postulate, the real path that this object takes minimizes something, just like light. Let's call that something S. For this to work, then S needs to take in a path and spits out a number, just like the travel time does, travel time of a light. The travel time doesn't only depend on the path though, the path x of t, but also the velocity v of t, or x dot of t, where dot denotes the time derivative. So let's guess that S takes in x of t and x dot of t, then spits out a real number. So what kind of mathematical object that does this? Which one is suitable for us? Okay, options. Our first guess might be that S might be just straight up a function of x and x dot, which means it is basically a function of time. To get a real number out of it, we just evaluate it at a specific time t. However, this only characterizes one point in the path, not the whole path. Two different paths could give the same number as long as they crossed each other, and we evaluate S at the time when they cross. So this won't do, it won't differentiate the two different paths. In fact, if we need to evaluate at just one specific time t, it won't do for our purpose. So perhaps a definite integral. It spits out a number, yes, after integrating and evaluating, but it also takes the whole path into account, not just the one specific point in time. Then let's guess that S is some definite integral dt from ti to t sub f of something again. Let's just call it L. L needs to take in the path x of t and velocity x dot of t. And this is it. This is exactly the foundation of Lagrangian mechanics, and S later called the action, and L is called the Lagrangian. So from here, okay, we got the action and Lagrangian. What about this famous Euler-Lagrange equation? This equation answers the question, what kind of x of t minimizes s? What kind of equation does it need to satisfy? Well, we need to turn to variational calculus, which I won't explain much, just enough for us to get by. On the surface, it behaves just like a regular total derivative of a function. When s is at its minimum, its derivative is 0. So we write variational derivative as delta, so delta s is 0. Before we continue, let me just explain one important detail about this variational derivative delta. This is a crucial detail for us later on. Going back to our picture, there's an object initially at x sub I with velocity v sub I, moves to a final state x sub f with velocity v sub f. Let's say that this is the actual path that the object takes. By taking the variational derivative, what we're doing is we take this path, then add some variation, delta x, to it. If this is really the actual path, then if we add a small variation delta x to the path, the action s would not change, meaning we have found a path that minimizes s. One key detail about this delta x is that, well, we know the object of initial and final position for certain, as we assume that it's given to us. It would not make sense if we also vary the endpoints. So it's common to impose the condition that delta x is 0 at t sub I and t sub f. Now, back to our derivative. Let's plug our s straight in and get the derivative operator inside the integral. I'm going to suppress the t dependence for now. Now, as I said, the variational derivative delta behaves pretty much like the total derivative of a function, so we evaluate it the same way. Now, I write down x dot explicitly as time derivative of x. This one might seem weird at first, but if we can't swap the delta and the time derivative. Here's a quick derivation of y. If we start with path x and we vary it, we end up with x plus delta x. Taking the time derivative, we get v plus the time derivative of delta x. But if we instead take the time derivative first, then vary it, we end up with v plus delta v, which is v plus delta of time derivative of x. So these last two terms should be the same. This might not be a rigorous proof to show this property, but this is used very often in variational calculus derivations that I've seen at least. Anyway, back to our equation. A trick to simplify this integral is to focus on the second term. It would be nice if the time derivative is acting on the whole term, not just the delta x. So let's check the time derivative of the whole term and see how it compares to our last term. These should not be partial derivatives, by the way. The time derivative of the whole term is this. I just used the product rule to get this. The last term in yellow is exactly the second term in white. So we can substitute the yellow one in. Let's then tidy it up, grouping the terms with the delta x factor and deal with the leftover. Now the leftover in yellow is an integral of a derivative, so we can use the fundamental theorem of calculus to evaluate this, and it's this thing evaluated to t equals t sub I to t sub f. Recall that delta x at initial and final time is 0, so this yellow thing is ultimately 0. So we're left with this curly fancy L should be just a normal capital L. Curly L will be for something else later. Wink. Anyway, we're left with this integral equals 0. Now, delta x is arbitrary when t is between the initial time and final time. So it is not necessarily 0. So the only option left for us is this thing in the square bracket equals to 0. This is exactly the Euler-Lagrange equation of the Lagrangian mechanics. Alright, now that we got here, the question was what kind of x of t that minimizes s? Or now that we have this equation, what x of t satisfies this equation? Well, it depends on how L depends on x of t and x dot of t. Classically, you know, it is t minus v, the kinetic energy minus the potential energy. But bottom line is, if we know L and we can express it in terms of x and x dot, we can find x of t. Okay, alright, this is all well and good. This should be a review after all. But what about field theory? Where field? That is coming up in the next video. I will do the same reasoning and derivation for fields, classical fields more specifically. I will discuss why the action S is an integral of over all space and time instead of just time, how Euler-Lagrange equation for field theory is derived, and later on I will continue with the quantizing the field, giving us finally quantum field theory. Until then, I hope this video helps. Thanks for watching.